I'm sharing my screen. We'll see the codes related to you see here. Some codes are there. Okay. First, I will tell you half adder by using data flow modeling, and next half adder by using data flow modeling and behavioral modeling if it's there. We'll see. Okay. This half adder by using data flow modeling and full adder by using data flow modeling and full adder by using structural modeling also we'll see. Okay. This is half adder by using data flow modeling. Okay. So here I wrote with this GB. So if you expand this, yeah, one second. Yeah. If you expand this, so module half underscore DUT, I need to declare input A comma B, output sum comma CA. These are wide data type. Assign, I need to use a continuous assignment statement. Assign sum equal to A XOR B. Assign CA equal to A and B and end module. Okay. This is the simple program for the half adder by using data flow modeling. Okay. And coming to this one, product TB is there. Okay. This is nothing but test bench. I need to write the test bench. Okay. So have you seen the port rule connections? So this is my module name. Okay. Verilog code will start with module and module name. Module half underscore TB. Whatever the inputs are there, that inputs you need to declare with wire data type. Some sorry, whatever the inputs are there, that you need to declare with reg data type. So reg comma, and whatever the outputs are there, you need to declare with wire data type some comma CA. And next, you need to instantiate the design. So as I explained in the RTL design, there are two types of instantiations are there. One is connection by name, and another one is connection by position. So this is nothing but connection by position. So how you declared the inputs in the design, the same order you need to declare in the this half adder, this connection by position with order list. Okay. Initial begin dollar display. So I want to display this A equal to percentage B, B equal to percentage B, and sum equal to percentage B, and C equal to percentage B. This is format specifier. A comma B comma. So you are displaying in terms of binary. So I need to give the stimulus, okay? A comma B comma sum comma C, and I am giving A equal to 1 tick binary 0, B equal to 1 tick binary 0. So after 10 time units, I am making A equal to 1 tick binary 0, B equal to 1 tick binary 1. So just I am checking, I am giving the inputs, and that is given to the design, and I am getting the outputs, okay? Dollar monitor is nothing but this is also a system task. If there any change in the outputs, okay, that will be displayed. Okay, every time there is any change in the outputs, that will be displayed. Okay, this is A equal to percentage B, B equal to percentage B, sum equal to percentage B, and the C equal to percentage B, A comma B comma sum comma A. So after 10 time units, I am giving the values A equal to 1, B equal to 0. Next, the dollar stroke also will find out what is the dollar stroke. And after 10 time units, A equal to 1, B equal to 1. So this simulation will be done for 50 time units. Okay, 50 time units, dollar finish and end module. Okay, this is simple Verilog code and test bench you are writing. Okay, and so for this, what you need to do means you need to open this Vivado tool, Xilinx Vivado tool. Just wait, it will take time to open that Vivado tool. here, like first you need to go to file and create the project. Okay. Next, and I'm giving the project name is adders. Okay, my project name is what? Adder circuits. Okay, adder circuits. Okay, adder circuits. So I need to create the path. Here, this is the path. This is my path. Okay. So training and development and you need to select the path. Whatever the programs are there that you need to make one folder and you need to create. My digital and Verilog course, ASIC 15, ASIC G15 offline Hyderabad and Verilog program. This is my project path. Go to next and project type is RTL project and next. So you need to create a source file. Okay. So for source file, just if you so in the GVM, if you press I means it will go to editor window. If you press escape means it will go to command window. Okay. So if you keep escape means it will go to command window. So shift colon means you can like if you want serial numbers means you can use SCNU means serial numbers will get. So I means editor window. Okay. And this module name is there, no? This module name. Just copy this and give the source file. Okay. Next. Constraints, this is optional only. Next. And by default, the part number, the FPGA part number will be selected. Next. And finish. Project is created. My project name is adder underscore circuits. Okay. So it is asking that module name is also same means okay. Module name also half underscore DUT and giving. Okay. Yes. Yes, sir. This one is not required. Close and here. This is the design source. Okay. This is the design source. And whatever the test bench are there, you need to write in the simulation source. Okay. So here I am writing the design source. Okay. So what is my design source? This is my program. Hope you understood the program. Simple data flow modeling I'm writing. Okay, half adder circuit. Just copy this and when you are doing in the company, this all will come not required. Just paste here. Okay. This is nothing but time scale. So each simulation time is 1 nanoseconds and the precision is 1 picoseconds. That is the precision. And save this design file. Save the design file. And next, coming to the simulation sources. So click on simulation sources, add simulation sources, add or create simulation sources, create the test bench file. Okay, what is my test bench file? So this is my test bench file. Half underscore TB. Okay, copy this and paste this. Okay, finish. And module name is also same. Okay, yes. Yeah. So my test bench is created. See here. My test bench is created. Okay. Next, this code is there, no? Just copy this. So this code, copy this, and paste here, paste here, and save this. So initially in the simulation sources, half underscore DUT is there. Okay, that is gone. Why? Because in the test bench you given you instantiated, no? You instantiated this design in your test bench. Okay, so this is connection by position with the order list. Okay, position by position with order list. Okay, order list. If you are making this forward slashes means the compiler will not compile. It will take as comment only. So wherever you want to write the comment, so you can write the forward slash. Okay. So I wrote the program for half adder. I wrote the test bench also. Next, what you need to do? Suppose I want to elaborate the design. Okay. how the design will be there. Okay, so just go to elaborate design and save this project. I can see the elaborated design. It will take time. So as I told you, know that synthesis, your code is converting into gate level netlist. So based on your program, it will convert that one into hardware, and that will be you can see in the elaborate design. Yeah, you got the off adder. No? Okay, you got the off adder. So that is XOR gate followed by AND gate. This is a simple order off adder. So when you are doing the data flow modeling, you will get the actual circuit. Okay. So if you want to see the simulation, run the behavioral simulation. If you want to see the simulation, run the behavioral simulation. Yeah, simulation. You are already seen the dollar display, no? So when A equal to X, B equal to X, and sum equal to X, C equal to X. So when A equal to 0, B equal to 1, sum equal to 1, carry equal to 0, and A equal to 1, 0, sum 1, carry 0, 1, 0, sum 1, carry 0, 1, 1, sum 0, carry 1. No, okay. So here you are getting sum 0, carry 1. Okay. Sum 0, carry 1. That you can see in the simulation also. So just you see fit to page. This yellow line, you can bring it to this side. A equal to 0, B equal to 1. Okay. Sum equal to 1, carry equal to 0. Fit to page, fit to page. So every 10 time minutes increase. Okay. So here, for 10 time minutes, A equal to 0, B equal to 0 means sum equal to 0, carry equal to 0. And A equal to 1, A equal to 0, B equal to 1 means sum equal to 1, carry equal to 0. And A equal to 1, B equal to 0 is sum equal to 1, carry equal to 0. And A equal to 1, B equal to 1 means what? Sum equal to 0, carry equal to 1. Okay, like this you can see the simulation. Okay, hope you understood how you are doing, seeing the simulation. Okay, and suppose next program, half adder is over. No? This is half adder using behavioral modeling. Behavioral modeling. One second. Yeah, we'll go with full adder. Okay, full adder. This is structural. Structural means what? First you need to write the program for half adder. Okay, first you need to write the program for half adder. After that, you can design the full adder by using two half adders and one OR gate. No, that is structural modeling. Okay, data flow modeling means normally like you are writing in terms of expression. That is nothing but data flow modeling. Okay, this is data flow modeling. Hope you are, so that means in terms of expressions, we already seen in the list sum equal to A XOR B XOR C and carry equal to A and B, B and C, C and A. Similarly, you can write the test bench also. So this is the test bench. Test bench you can write. So output will be what while data type it will be rich data type. You need to instantiate and you need to give the stimulus test cases you need to give. Okay. So the data flow modeling okay. I will try with structural modeling. See here. I will try with structural modeling. Mm. So first you need to write code for half adder. No. First I think here this is half adder. Okay. Yeah. Okay. I'm writing the code for half adder. So expand this. So this is, yeah, this is half adder. Module half adder S comma C comma X comma Y. This is style work. Means you are declaring the ports inside the bracket, and separately you are initializing that input X comma Y, output S comma C. And this is nothing but gate level model. I am using the gate level primitives XOR and. So how the gate level primitives are there? I told you the gate level primitive output and input. Okay, S comma X comma Y, C comma X comma Y. Okay, this one. So just close this simulation, close this elaboration. Okay, and here what I need to do is this code just this half adder is there, no? This half adder, copy this, and in the media playground, go to design source, add this. Okay, add the design source. Okay, create file. What is my design source? Half adder. Okay, finish. Yes, my design source is created. Okay, so here you copy this code. First you need to write the design main design, that is half adder. Okay, so paste this, save this, and after this full adder. So this is the code for full adder. Okay, so if you see the full adder circuit, module full S comma C comma X comma Y, input X Y Z, output S comma C. And I told you how to implement the full adder by using two off adders. You need to indicate the intermediate wise, that is S1, D1, and D2. So you need to instantiate that half adder. Okay. So connection by position with order list I need to instantiate. How many times? Two times I need to instantiate. Half adder HA1, S1, D1, X comma Y. Half adder HA2, S, D2, S1, and Z. Or or gate is G. C1 is the output. D1 and D2 are the inputs. Okay. So this is the program structural modeling. So just first you full modeling, then just copy this and go to design source, create the design source, create file, full. My module name is full. Finish. Module name is full. Yes, yes, full. So full. Oh, this one. This code, no? Just and paste here, and save this. Now see, have you observed that means full is created, you instantiated, okay, you instantiated two half adders, no? In this half, that means in this full adder, two half adders are instantiated. Okay, initially I wrote the half adder code, and during the structural, by using the structural modeling, I wrote that means I instantiated two half adders. Okay, that half adder is instantiated into this full. Okay, that half adder is instantiated into this full. Okay, and after that, you need to write the test bench, full TB. So this is the test bench. So just yeah, 16. Module TB, outputs are with wide data type and inputs are rich data type. I need to instantiate the full instance. Okay, connection by position with order list. Initial begin. Okay, when you are writing the so you need to use the initial in the test bench, and multiple statements are there. You need to write between the begin and end. Okay, dollar monitor. If there any change in the output, it will display. So I am giving the test inputs. Okay, the random inputs I am giving. So x equal to 0, y equal to 0, and z equal to 1. 0, 0, 1 I am giving. After 10 timestamp, what I am giving, x equal to 1, y equal to 1, and z equal to 1. After 10 time minutes, I'm giving 101. After 10 time minutes, I'm giving 111. Okay. And dollar stop is for pausing the simulation, or here you can use dollar finish also. So for pausing the simulation, you can use dollar stop, or to end the simulation, so you can use dollar finish also. So how many time units I need to execute? One, two, three, four. Four means after 50 time units, I want to end the simulation. So dollar like hash 50 I can give. Okay. So module TV, copy this, and in the simulation source, add this simulation source, create TV. My module name is TV. Finish. Okay. Yes. Okay. TV is created. Okay. TV is created. This which file? One second. This file. This file. Copy this. One second. Copy this. Paste here and run this one. Save this. Now my TB file is created. Okay. My TB file is created. So here we are getting this three dots means this will be in the top module. Okay. So whatever the module I want to simulate, so right click, I need to set as top. Then it will become top module. Initially half underscore TB is top module. So now it becomes top module. Okay, I can simulate this. Okay. Anyway, in the design source, it is in top module only. Okay. Suppose if I want to elaborate the design, I want to see the hardware. Okay. So open the elaborated design. So I wrote the full adder circuit by using uh, structural model, by using instantiation. Okay, I wrote the half adder and I'm calling two times and one more OR gate. Okay, so like that you can design the parallel adder also. Here we carry adder, carry located adder, VCD adder. See here, this is my design. Two half adders followed by one OR gate. See here, if you press here, this is one half adder, and if you press here, this is one more half adder. Okay, so this is my elaborated design. Okay, and next run simulation, run behavioral simulation, run simulation, run behavioral simulation. Yeah, if you see here, so it's equal to, you can run in 1000 nanoseconds. So you can dollar monitor is given, no? So if there any change in the output, it will display. Okay, x equal to 0, y equal to 0, z equal to 1. 0, 0, 1 means what? Sum equal to 1, carry equal to 1. 1, 1, 1, sum 1, carry 1. 1, 0, 1, sum 0, carry 1. 1, 1, 0, sum 0, carry 1. Okay, you can see in the simulation also. So just to elaborate, hit to page, and here if you see 0, 0, 1, someone carry 0. Every time within 10 minutes. 1, 1, 1, someone carry 1. And 1, 0, 1, some 0 carry 1. And 1, 1, 1, 1, 0. So 1, 1, 0 means some 0 carry 1. Okay. So like this, you can see the simulation for the full adder. This I designed the full adder by the structural model. Okay. Hope you understood. And next, we'll go to multiplexers. Okay. File, project, open, multiplexers. No. One second. Multiplexers. This I'm opening. Multiplexers. Okay. Yes. Similarly, subtractors also same thing. You can write with uh, data flow modeling, behavioral modeling, and structural modeling. Okay. This is 2 cross 1 mux using data flow modeling. Okay. So 2 cross 1 mux. Hope it is visible. 1 second, I will zoom this. Yeah. See here. 1 second. So here this is mux 2 cross 1 data flow module. So module mux 2 cross 1 data flow. Input wire A, input wire B, input selection and output wire Y. Okay. So all are in wire data type only. Okay. So I need to use a conditional or ternary operator. Assign y equal to what? During the operators I explained. Okay. I need to use a continuous assignment statement that is assign. Okay. Output y equal to what? Select. If select equal to 1, B is connected to the output, okay, or else which is connected here, okay. With one statement, I can write the code for the multiplexer, okay. So this is nothing but data flow modeling. Coming to the test bench, here, 2 cross 1 mux, 2 cross 1 mux data flow, PB 2 cross 1 data. Cross 1 data flow is not there, okay, okay. This is data flow, okay. Case if is there, okay. Next, by using case statement, case statement, module marks 2 cross 1 case statement, okay, underscore case statement, input wire A, input wire B, input wire selection, output wire Y. So when you are using behavioral modeling, so I told you in the behavioral modeling you use a procedural statement like if else case statement, no? So output Y, output you need to declare with rich data type. Always at the rate star begin case select. Okay, case select. One tick binary 0, y equal to a. So that means when select equal to 0, y is connected to a. Okay, when select equal to 1, y is connected to b. There is a default statement in there. Okay, for default statement you need to write in the case statement. Why? Because when you are not writing default statement, it will infer as a latch. Okay, it will assume that as a latch. Okay, default statement will be there. Default y equal to 1 tick binary x, end case end. Okay, this is by using case statement. And 2 cross 1 mux by using case statement test bench. Okay. Data flow is also there. See here. Data flow. 2 cross 1 mux data flow. See here. Module TB. Reg A, comma B, wire Y. I'm instantiating connection by name. This is nothing but connection by name. Okay. Whatever the variables outside the bracket are nothing but design inputs and outputs. Whatever the variables inside the bracket are nothing but test bench inputs and outputs. Okay. Integer I. So I want to display dollar display select A comma B comma Y and this one display. Here I am using for loop. For loop. Why you are using for loop means how many inputs are there? 3 inputs are there. So 2 cube. 2 cube means 8 possible combinations I can check. Okay. For I equal to 0, I less than 8, I equal to I plus 1. Okay. I plus plus will not take in the Verilog. I equal to I plus 1 you need to give. I am using concatenation operator select comma A comma B equal to I for every 10 minutes and you want to display and dollar finish and model. Okay, so this is the data flow modeling test bench and if else statement also. See, if else statement, this is the code for if else statement. So means the declaration is same only, input A B selection and output reg Y. Okay, always enter star implication operator. So here you can use A or B or selection, or you can use star also. Okay, begin. If select equal to 0, y equal to A, else y equal to B. Okay. Similarly, the test bench will be same only. Where you get the change means in the instantiation you will get the change. The remaining all are same only. Okay, in the instantiation, the design will change. Design name will change. Okay. That is 2 cross 1 mux. So this one, suppose 2 cross 1 mux. Okay, case statement I will see. Okay, case statement. If you want to see the design, set as top and TB also. 2 cross 1 mux case statement. Case statement. Case statement 2 cross 1. So I want to simulate this. You need to set as top. the touch and so um, you need to elaborate the design. You need to see the design, how the design will look like using case statement. Yeah, this is the mux, my elaborated design. Okay, A, B selection, S and Y. Okay, this is my elaborated design. Run simulation, run video simulation. So you can see in the TCL console the output. Okay, so I am checking all the possible cases. Means what? 8 possible cases. Okay, when selection equal to 0, which one will be connected to the output? A is connected, no? So y equal to what? That is whatever the A value is there, you are getting 0, 0, 0, 0, 0, 1, 1 you are getting. Okay, when selection equal to 0 till here. Okay, till first four cases you are getting y equal to what? Okay, next four cases when selection equal to 0, output is connected to what? B. Okay, whatever the B value is there, you are getting 0, 0, 0, 1, 1, 0, 0, 1, 1. Okay, like that you can see in the TCL console, or you can see in the simulation also. Okay, expand this fit to page and bring this side. Okay, so till here A equal to 0, B equal to 0. Okay, selection equal to 0, Y equal to A only connected. Okay, whatever the A value is there, that you are getting at the output. Okay, whatever the A value is there, you are getting at the output. Okay, till how many? 4 means up to 40 you are getting. Selection equal to 0 means y equal to e you are getting. After 40, y equal to b you are getting. Okay? So selection equal to 1 means what? Output is connected to b. Okay? And you see here, output is connected to whatever the b value is there, you are getting it to the output y. Whatever the b value is there, you are getting it to the output y. Okay? So this is like this, you can see the simulation and elaborated design for the 2 cross 1 mux. Okay? And suppose if you see the 4 cross 1 mux, 4 cross 1 mux means if it is data flow modeling means normally you will get. But 4 cross 1 mux by using if else and case statement. Okay, this is if else statement only. Okay. So 4 cross 1 mux means how many inputs are there? 4 inputs are there. Okay. So 4 inputs. Okay. So 4 inputs means how I declare means by using the vectors concept. Okay. Input y the I'm declaring the d variable with 3 down to 0. 3 down to 0. So here I can use the vector concept. So 3 down to 0 means how many inputs are there? 4 inputs are there. Okay. And selection, 2 selection lines are there. So I am declaring while 1 down to 0 selection. Rather I'm using behavioral modeling, output should be declared with rich data type. Always at the rate star begin. If selection equal to 2 tick binary 0, y equal to d of 0. Else if selection equal to 2 tick binary 0, 1, y equal to d of 1. Else if selection equal to 2 tick binary 1, 0, y equal to d of 2. Else. So else means the last statement will be selection equal to 1 tick binary, 2 tick binary, 1, 1 only. Okay, no need to write that. Okay, that's why else y equal to d3 and end model. Okay, so this is a code by using if else statement. Okay, and suppose code using case statement using case statement. One second, we cross one box. Case statement. This is case statement. Okay, see the case statement module mux 4 cross 1 case. So 3 down to 0, D0 to D3, and selection lines are 2, 1 down to 0. Range Y, always at the start, case selector. 2 tick binary, like truth table only. 2 tick binary 0, 0, Y equal to D of 0. 2 tick binary 0, 1, Y equal to D of 1. 2 tick binary 1, 0, Y equal to D of 2. 2 tick binary 1, 1, Y equal to D of 3. Default Y equal to 1 tick binary X. Okay, there is will be, for every case statement, there will be default, default statement. End case, end mode. Okay. Suppose if you observe when you elaborate this design using the if else and case, there will be a difference. Okay, suppose I'm elaborating this 4 cross 1 mux. I'm setting a stop. I'm setting a stop. Okay. Mm, now 4 cross 1 mux set as stop. Just to see the elaborate design. See here. So it is looking like a priority mux. Okay. So if else statement means the compiler is converting your program into like priority mux. Priority mux we already discussed. In the digital we already discussed the priority mux, two cross one mux. Like these levels are there. Okay, it is showing like a priority mux. Okay, when you are writing the code in if else statement, suppose when you are writing using case statement, four cross one mux, right click, set as stop, set as stop. Open the elaborated design. See, normal marks you are getting. So when you are writing the code using if else statement, you are getting like a priority marks. When you are writing the code using this two class, by using case statement, you are getting normal marks. Okay, that difference you need to identify. Okay. This is about the marks. Okay, similarly you can write for. I wrote the 8 class 1 marks by using data flow modeling, 8 class 1 marks using so data flow modeling means if selection equal to 3 tick binary 000 question mark D0 colon 001 D1 colon 0010 colon D2 like that. Okay, or colon 1 tick binary X. This is nothing but I need to use the data flow modeling. I need to use the continuous assignment statement. This is case statement, if else statement. Okay, this is normal if else statement and this is the normal case statement. Okay, 8 inputs, sorry, 8 inputs, 1 output, and three selection lines. Okay, so this is 8 classroom. And next we'll see the just a basic idea I'm giving. Comparator we'll see comparator. So in comparator we already studied how many bit comparator, 1 bit comparator and 2 bit comparator is there. I'm opening that. Yeah, this is the comparator, 1 bit comparator. Okay, this is 1 bit comparator. So 1 bit comparator, how many inputs are there? You have two inputs and three outputs. Okay, two inputs are A comma B, and three outputs are. So I'm using behavioral modeling. I need to use output with reg data type. Reg equal, that is equality output. Reg greater than output. Reg less than output. Okay, output I need to initialize with equal greater less than. Okay, and always at the rate ARB. Okay, this is the sensitivity list. Okay, if there are any change in the input, then there is the change in the output. Okay, always at the rate ARB begin. Okay, multiple statements you need to write between the begin and end. If A equal to B, begin equal to what? 1, greater equal to 0, less than equal to 0, end. Else if A greater than B equal to 0, greater equal to 1, E greater less than equal to 0, and else begin equal to 0, greater equal to 0, less than equal to 1, end. So this begin I need to end. And after always at the rate this begin is there, no? This begin I will okay end module. Okay. Coming to the test bench in the simulation. So 1 bit comparator. You see the test bench. Module TB comparator 1 bit. Reg A comma B. While equal to greater less than comparator. So I'm instantiating connection binding. So what are the variables outside the bracket are nothing but design inputs and outputs, and whatever the variables inside the bracket are nothing but experiment inputs and outputs, initial begin. And I'm using dollar monitor. Dollar monitor means any change in the outputs it will display. Okay. Dollar time also. Time is one data type. Or time also and display. If I want to display the time, time equal to what percentage t, and e equal to percentage b, b equal to percentage b, and equal to percentage b, gt equal to percentage b, lt equal to percentage b, comma dollar type a b equal to greater than okay. So I'm giving the test cases. So a equal to 0, b equal to 0 means what? After 10 times, so 0 means equal. You need to get equal to 1. A equal to 0, b equal to 1 means after 10 time minutes. I need to make this delay also 10 time minutes. Okay. Less than equal to 1. A equal to 1, b equal to 0, greater equal to 1. A equal to 1, b equal to 1, equal to 1. And finish, dollar finish. Okay. This one I want to execute. Okay. So one bit only. No, this is the top model. Run simulation, run behavior simulation. So if you see the output, see here, it one run for 1000 nanoseconds. A equal to b equal to 0, equal to 1, greater 0, less than 0. A equal to 1, b equal to 1, equal to 0, greater 0, less than 0, less than 1. A equal to 1, b equal to 0, greater 1. A equal to 1, b equal to 1, equal to 1. Okay, you can see in the simulation also. Just hit to page. And every time, 10 time minutes, you see here. Bring this yellow line. A equal to b equal to 0, equal to 1, a equal to b equal to 1, less than 1, a equal to b equal to 1, greater 1, and a equal to 1, b equal to 1, equal to 1. Okay, so you can see it like this also in simulation window. Okay. Similarly, you can see in the 2-bit comparator also. 2-bit comparator means what? The same code, but two inputs you need to declare with vectors. Two inputs we need to declare with vectors, 1 down to 0. So two inputs are there, no? So 1 down to 0 and A, 1 down to 0 B. Okay. So remaining code is same only. And to take binary, here this test bench is also same, but test cases here you need to instantiate the design, and after that you need to give the test cases, that is 0 0 equal 0 1, two bits you need to give. Okay, 1 0. Random test cases you need to check 1 0 1 0 0 1 1 1, like this you can check. Okay. This is about the comparator, and we'll see the decoder, and we can wind up. 1 second, I'm opening the decoder. 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 2 to 4 decoder, 3 to 8 decoder. Okay. 2 to 4 decoder means how many inputs? 2 inputs, and how many outputs? 4 outputs. Okay. So here if you see the code, just I declared first module decoder 2 to 4. How many inputs? 2 inputs. Now I am using vector concept 1 down to 0. Input enable. Output 4 outputs are there. I need to initialize with range data type 3 down to 0 out. So this is a module declaration, and always at the rate in or in enable. If there any change in input and enable, begin. Okay. Enable is nothing but we saw that truth table in the digital. When enable equal to 0, that will be inactive state. Okay. When enable equal to 1 only, it will be in active state. Okay. So that's why enable is also one more input. Okay. If enable begin case in, okay, case in 2 tick binary 0 0, out equal to what? 4 tick binary 0 0 1, and 2 tick binary 0 1, out equal to 4 tick binary 0 0 1 0. At a time, any one of the output will be 1. That is related to this binary representation. Okay. That binary representation means this is in 0, and then is in 1, in 2, in 3, like that. Okay. So 1 0 means 0 1 double 0, 1 1 means 1 0 0 0. Default is how much? Default statement also there for case statement. 4 tick binary 0 0 0, and case and else. Else means what? If enable equal to 0, output will be disabled to 0. Okay, this is the behavioral modeling for 2 cross 1 mux. And coming to the test bench, 2 to 4 decoder. So here my module name module TB underscore decoder 2 to 4 decoder. Inputs I need to declare with rich data type. Input 1 down to 0 in rich enable. Wire I need to declare with output I need to declare with wire data type 3 down to 0. Next I need to instantiate the design. Okay. So what is my design name? Decoder underscore 224 UUT in enable out and dollar monitor. So initial begin dollar monitor means what? If there any change in the outputs, it will display. Okay. So time also time also I am giving. Okay. And enable equal to 0. So it will be disabled state only. So when enable equal to 0, whatever the input you are giving, it will be output will be 0 0 only. When enable equal to 1 only, then it will be in a functional mode. 0 0 means out is 0 0 0 1. 0 1 means 0 0 1 0. It is 1 0 means 0 1 0 0. In equal to 1 1 means 1 0 0 0. And again I am making one enable equal to 0. Whatever may be this input, you are getting disabled. Enable. This is disabled. 1 0 or 1 1. Okay. If it is XX, enable equal to 0, the decoder will be disabled. Okay. Based on the enable signal only. So this one, so just set a stop model. It is stop model only. Um, Elaborate that is run the simulation. Run the simulation. Run behavioral simulation. Save. You see in the TCL console, you will get see here. When enable equal to 0, in equal to 0 0, out equal to what? All zeros only. Okay, it will be in disabled state. Decoder will be in disabled state. When enable equal to 1, in equal to 0 0, so out equal to 0 0 0 1. And enable equal to 1, in equal to 0 1, out equal to 0 0 1 0. And in equal to 1 0 0 1 0 0, 1 1 0 1 0 0 0. Again enable equal to 0, in equal to 1 0, out equal to 0 0 0 0. Okay. You can see in the simulation part also. Just to expand this fit to page. So here, so here, this is if you right click, so right click and you can see in the binary also in the waveforms, wave style, digital, digital. You can see the waveforms in the wave style, signal color. Mm, yeah, see here. 1 second. Radix. Okay, radix is default means what you are getting in a decimal. Suppose if I want binary means you can write here. Right click radix. Radix binary. It will show in terms of binary. Okay. It will show in terms of binary. Bring the yellow line here. Okay. See here. When enable equal to 0, whatever may be the input, you are getting output equal to what? 0 0 0 0. Okay. When enable equal to what? When enable equal to 1, input is what? 0 0. The output is what? 0 0 0 1. And input is 0 1. Okay. Input is 0 1 and output is 0 0 1 0. Input is 1 0. Output is 0 0 1 0. Okay. Input is 1 1. Output is 1 0 0 0. Okay. Again you are making enable equal to what? Enable equal to 0. Enable equal to 0 means what? The decoder is disabled and output making as 0 0 0 0. Okay. So like this you can see the simulation waveform for decoder. Like this same encoder also. Okay. Encoder also.